Today's lecture, students, is about calculating the average atomic mass of a particular element. And I've listed here the CUDs for this lecture. So let's just go over these real briefly here. You will need to know that the atomic mass is the mass of an atom measured in atomic mass units. Hopefully you know that already. And several students have asked me about the term abundance. Abundance means the amount of something. If there is a large amount of something, we say that it is abundant. And for example, at Thanksgiving, we celebrate and are thankful for an abundant harvest, which would mean that hopefully the harvest of the crops produced a large amount of those crops, and we will all have plenty to eat during the winter. Okay, so the thing you need to understand that by the end of this lecture is that the atomic mass of an element is a weighted average mass of all the different isotopes of the element based upon their relative abundance. So when you have a particular element, the amount of the isotopes of that element is not equal. They're not equal to each other. So some isotopes are more abundant than other isotopes. And then by the end of this lecture, you should be able to state which isotope of a particular element is more abundant, given the average atomic mass of the element and the atomic masses of the individual isotopes. We will go through an example of that. And you should be able to calculate the average atomic mass of an element given the atomic masses of the individual isotopes and their percent abundance. And we will work through an example of that as well. Okay, before we get started with elements though, let's talk for a moment about grade point average. A grade point average is an example of a weighted average. So you are probably aware that each grade is assigned a numerical value from 0, and that would be an F, to a 4.0, which is obviously an A. Now imagine a student who only gets A's and B's in classes. If that student's grade point average is 3.25, did he earn more A's, which would be a 4.0, or more B's, which would be given a 3.0? Well, it's probably really obvious to you that the student would have earned more B's in his classes. Why? Well, think about it. His grade point average of 3.25 is closer to the numerical value given for B's than it is to the value given for A's. So we could easily look at this example and say, yeah, he earned more B's than A's. And B's on his report card would be more abundant. Aha, we've used that term again. Okay? So that was an easy example. Now let's get back to the elements. Copper has an atomic mass of 63.546 atomic mass units, AMU. Copper has two isotopes, copper 63 and copper 65. Which isotope is more abundant? Well, let's look at this average atomic mass, this weighted average here. Is this value closer to 63? Or closer to 65? Well, it's closer to 63. Therefore, most of the copper isotopes must be the copper 63 isotope rather than the copper 65 isotope. So this one, copper 63, must be more abundant. Okay, once again, this copper 63 would be more abundant because the average atomic mass is closer to 63. That means when you were adding up all of those isotopes, there were more 63s to add in than 65s, just like there were more Bs on the report card than As. Okay, now to calculate the average atomic mass of an element, here's what you need to do. You need to multiply the mass of each isotope by its relative abundance. And we're going to express that as a decimal fraction. And then you add the products. Now, hopefully this sounds a lot like the penny lab we just completed. Okay, so think about this for a second. If we had in the pennies, if we had 4 pennies at 3.5 grams. Oh, those were 3.1 grams, weren't they? Let's say 3.1 grams. And we had 6 pennies at 2.5 grams. The 2.5 gram penny would be more abundant, right? Okay. And then we would have a total of 10 pennies here. So 40% of the pennies would have this mass. 60% of the pennies would have this mass. And how would you determine the average mass of this pile of pennies? Well, we would multiply 3.1 times 0.40. Okay, because that's the decimal fraction of 40%. And we would add to that 2.5 grams times its percent abundance, 0.60. And if we do that, my calculator, 3.1 times 0.4 is 1.24, and 2.5 times 0.60 is 1.5. We add these together, and our final answer is 2.74. Now that would be the average atomic mass of 1 penny. So let's say we're talking about pennium elements here, we would give that units of AMU. Okay, so that's how we would get the average atomic mass of this particular set of pennies. Okay, we're going to use the same principle and look at real elements this time. Now, hopefully you can read this slide, but what I want to show you here is that the first sentence is exactly the same sentence that I had on the previous slide, only smaller. But then I've listed the information for bromine. Bromine has 2 isotopes, bromine 79 and bromine 81. The masses of the isotopes are 78.92 and 80.92 AMU respectively. That means these masses are listed here in the same order that I've listed the isotopes above. Okay, so this mass is for this isotope, and this mass is for this isotope. Now I'm going to erase that because I've covered up my percentages. Likewise, the percent abundance for the isotopes is 50.69 for this one and 49.31% for this one. Okay. So how would we calculate the average atomic mass? That's exactly the same way we did it for the pennies a moment ago. So we would need 78.92 AMU times its percent abundance, or its abundance listed as a decimal fraction. So we would change this percent, move the decimal place over 2 places, and make that 50 or 0.5069. Then we're going to add the products. We need to add to that. So let's put this in brackets. We're going to add to that the product of the mass, 80.92 AMU, times its abundance as a decimal fraction. We're moving the decimal point over 2 places. So 0.4931. And close that bracket. And then we're just going to solve this, and our answer will be the average atomic mass. So let's just do that. This 78.92 times 0.5069 is 40.00. And 80.92 times 0.4931 is 39.90. Okay, we add these together and we get 79.90 AMU. Now, if you look at the periodic table for bromine, you will see that the average atomic mass for bromine listed on the periodic table is 79.904. Okay. And this is very, very close to 80. And I want you to notice that 80 would fall right between 79, would be halfway between 79 and 81, right? And look at our percentages. Our percentages are very close to 50% each. Okay? So yes, if you had half at 79 and half at 81, then you would get an average atomic mass of very close to 80. And sure enough, that's what you get. So that is a very logical answer. Okay, I have one for you to try. Lithium also has 2 naturally occurring isotopes. Here are their masses, and here are their percent abundances. I want you to try determining what the average atomic mass for lithium is. You need to show all your work and bring that with your notes to class tomorrow.